Hello all. In this video, we're going to do a little bit of review and then do a little more detailed examples involving algorithms and pseudocode, especially pseudocode, because I know sometimes that can sound mysterious and it's really easy to uh, overcomplicate it in your head. But I want to talk a little bit about what it is and why we use it, and then do some examples together. So here we're just going to start. So yes, I want to remind you of what an algorithm is because algorithms and pseudocode go together a lot. We'll talk about what pseudocode is and how it relates to algorithms. We'll talk about why we use pseudocode in a little more detail than we've done in the past. I'm going to look at some examples of pseudocode that you have already seen that you may or may not even be aware of. And we're going to then work through two examples showing how to write pseudocode. All right, so starting with what an algorithm is. We started with this at the very, very beginning of the semester. It's an idea or a concept. An algorithm is not a program, but it is a description in any form of a process for solving a problem, a step-by-step detailed process. So it can be a program. That's one of the ways we can represent an algorithm. We can also represent an algorithm with a diagram, with pseudocode, or in other forms as well. So if you remember at the very beginning of the semester, we had some examples of daily life or things in your previous experience where you have worked with algorithms, even if you didn't realize it. So things like a recipe for cooking something is in a sense an algorithm. It's step-by-step instructions for how to cook something. And part of that, of course, is also that we need to have a list of ingredients, the data that we operate on. And that's going to be also a theme throughout many of these things that we consider are actually algorithms. There's information or objects or data that we're operating on. And then there are the step-by-step instructions on what we want to do to that. But the idea of a process is really key here. So cooking recipes, assembly instructions, how to put together a new chair you just bought at a store, driving directions, so how to get from point A to point B, arithmetic operations that you may have learned back in elementary school, how to add two multi-digit numbers together. There's a process to doing that. You have to do it right or you get the wrong answer. And so we have an algorithm that was taught to you most likely without using that word, for exactly how to do it correctly. All of those are great examples of daily life algorithms. In computer science, we have whole courses that focus on algorithms to solve a wide variety of different problems. But there are a couple of details that we're looking for that lead us into wanting to have and use pseudocode. So we want to be able to think about the process, the algorithm, separately from any particular programming language. Each programming language has its own kind of unique idiosyncratic syntax. It has specific tools that it provides that may be different from another programming language, but the underlying algorithm is an idea, it's a concept. It's not tied to those specifics of any one particular programming language. So one of our goals for having pseudocode is that we would like to not specify every process that we talk about in a specific programming language. We'd like to be able to do it in a form that's more generic, that could be applied to many different programming languages. And that gets to the second point here. We'd like to be able to translate an algorithm into any programming language. And the more specific you make it to one language, the more changes you have to make that aren't important to the idea, that are just about how you encode that idea when you want to transfer it to somewhere else. Programming languages also are designed to be understandable by computers. In order to make it possible to write interpreters and compilers, we make some compromises, some concessions to the needs of the computer. They need things very specific ways that you can't have any flexibility in notation because otherwise it just gets too complicated to actually turn your program into something that runs on the computer. So a programming language is not designed to be easily understood by humans. It's designed to be easily understood by the computer, and then we learn how to speak in that programming language in order to create our programs. So we would like to be able to describe algorithms in a way that's easier for humans to understand. That is the goal of pseudocode. Pseudocode is for communicating algorithmic processes in a form that is easier for humans to understand. All right. So that's why we want this thing that's the purpose of pseudocode, really, but what exactly is pseudocode? Now, I will warn you, if you go out on the internet and you just start looking for things that introduce pseudocode, you will find places where they specify these rigid rules for exactly how pseudocode should look. Those are not actually widespread. There's not one agreed upon way that you write pseudocode. It is, in fact, extremely flexible and really only has certain limitations or certain formalisms that are common. And so you won't necessarily find unity about exactly how you should write it. But that's because there isn't any more than there's unity about exactly how you should phrase sentences in English when you write an essay. Pseudocode is for people. It has the flexibility of our natural language on purpose. And it's okay to come up with your own variations on the notation. You don't have to follow a specific formalism. All right, so pseudocode is a step-by-step description of an algorithm written for human use, not machine use. So what do we mean by that? It usually describes a single algorithm or process, and often we conceive of that, we think about that as a function. So we imagine that we're going to write a function, and here's this algorithm that sits in its place. It doesn't always have to be the case. You can write an algorithm that's more script-like in its layout, and that's just fine as well. It's just that often we'll describe them using a similar syntax to what we use when we define functions in a programming language or methods. Typically, pseudocode is a combination of a number of things. It has numbered steps, and how you number it may vary from one formalism to another, but typically there's steps that are numbered 1, 2, 3, 4, 5. It uses English descriptions and mathematics notations, when those are appropriate, to describe what to do. And it does allow for code-like control structures. In particular, we use if statements, conditionals, and we use loops that might look kind of like for loops or while loops, which we're going to learn fairly soon. You can also do things like variable assignment. That's perfectly fine. You can have a statement that looks like a print statement and so forth. So we can incorporate pieces of code-like notation without it being tied necessarily to any particular programming language. So in fact, we try often to avoid using things that are very specific to certain programming languages. So for instance, if some of you know Java, or you might know one of the other languages that are related to it, and those languages have a particular form for adding one to a variable, which is that you're allowed to just say plus plus after the name of the variable or before it, and an addition of adding one to that variable happens. That's very specific to those languages. Most other languages don't do that, so we don't want to use that when we write pseudocode because it's not general, and it's not a notation that a non-programmer would make sense of. So we want pseudocode also to be accessible even to people who don't program in any particular programming language. We focus on logic and meaning, and what is the meaning of each step, and not exactly how you would perform that step in any particular language. But we do want our steps to be detailed. We want this to be detailed enough that we can look at each step in the pseudocode and say, yeah, that's something I think the computer could do with 1 or 2 lines of code realistically. You don't want to have a step that would take 100 lines of code to actually implement, because then you're skipping over all of the detail and you're not really explaining how this is actually going to happen. But what I put in bold here is the main point. There are no fixed rules for what pseudocode should look like, and you can ignore any online sources that suggest otherwise. All right, so why is pseudocode useful to us? I tried to get at this a little bit earlier, but let's take another look at it. I see really two reasons. One is related to communication, and the other is related to design. And they're both important reasons why we want to use pseudocode. The first one is the one I've already talked about. It works better to read and write pseudocode with other people when you're talking about a process and how it should work. Writing out the steps in pseudocode is faster and easier, especially if you and the person you're talking to aren't necessarily fluent in the same specific language. Sticking to pseudocode lets you communicate better. It's easier to write, ideally, and it's something that is easier to read for us human beings. The second reason is also critically important, and it gets at why we are emphasizing pseudocode in this class. When you go to write a program of any scale, whether it's just a short 3 or 4 line script or a 100-line or a 1,000-line program that you write later on in your career, it always works better if you take seriously a step of design before you start implementing your code. So it's easy at the beginning, and often with the simple examples, I can just sit down and, as an experienced programmer, I can just sort of think about how I want to solve the problem, and I can start typing. And I can type out the code. Because I've programmed so much for so many years in these languages that it's almost second nature to me. Not always, but sometimes. But that's not our usual situation. And especially when you're starting out, having your thoughts clear and straight in your head, that you've worked out what the process should be, what the algorithm should be that you're going to try to do, this is actually really important. Sometimes, when you're working on an assignment we give you as a beginner, we may give you some support. We may go through the steps that you need to implement, where we've already worked out the process, and then we just tell you how to do it piece by piece so that you can implement a little bit and then test, implement and test, and so forth. But when you want to write code on your own, or at times because we know that it's good for you, we are going to ask you to take the time to design your code before you start writing it in a given programming language. And that's because there are two things getting tangled up when you try to do both at once. One of them is that process, the algorithm, and being clear on what the steps are you want to accomplish. And the other is being able to articulate in the programming language the things that you want to do. Those are actually two separate things. If you just sit at the keyboard and start typing, you're doing them both at once. And as a beginner, that can often lead to confusion and frustration, where you're writing code but you're not exactly sure where you're going with it yet, and you're just kind of trying things. Or on the other hand, where you know what it is you want to do, but you struggle to turn it into actually working code. So design is important. It helps us. So I have a couple of bullet points here, just to sort of talk about what you should be thinking about. It's easier to describe something in English than it is to write correct Python code. We can work out our thinking how to solve the problem without actually thinking about code. And once we've worked that out, then when we sit down to program, our task becomes translation. We're translating something we already have into Python, in our case, into our programming language. That's way easier than coding from scratch where you're trying to do the design and the coding all at once. So I have one little analogy here that I'll just leave this with, and then we'll go on and work out some examples. We'll take a look at some examples you've seen before. Imagine that you are in a situation where you need to communicate with someone in a language that you're not very strong in. You know a little bit of it, but you're not particularly fluent, and it's something complicated. You might not want to just jump into that conversation and wing it. What you might choose to do is to sit down and write out in your own native language what it is you need to say, and then translate that before you start your conversation. So, sort of the same thing that we're doing here. Figure out what it is you want the computer to do in pseudocode, and then translate that pseudocode to Python. So I have some examples that I've drawn from earlier assignments. Some of them were labeled as pseudocode at the time, and this first one is an example. So this was from our first homework assignment. This was me writing out an example of a pseudocode algorithm, and then saying, well, you could follow this kind of a model. And you absolutely can follow this kind of a model if this makes sense to you. So what's important to see here? One is that I have a top line. This is where I say we kind of conceive of these algorithms as functions. This is very similar to the top line of a function definition that we might write. It has the word algorithm, it has a name for the algorithm, and it has a list of inputs. And then right after that, I have put a little comment. This is not a comment format that's actually used in any programming language. I just thought it stood off well compared to the lines of instructions that I had, so I chose to use it. So this just describes what it is that the algorithm that's coming up is supposed to be about. It takes in an image and a color, and it draws 3 squares with sizes 10, 50, 100, and 150 centered in the image. Okay, so this is supposed to draw 3 squares on an image. Boom, 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 getting bigger each time. All of them of the input color. So then I've worked out, in this example, I worked out the steps for this algorithm first, just writing them out in English. So find out the width and height of the image. How do you do that in Python? It's kind of intricate. There's a lot of arcane symbols there. This makes a lot more sense to someone who doesn't really get Python yet. Finding out the width and height of an image, that's something you can imagine that a computer can do, even if you don't know how to do it in Python. We need to calculate the middle of the image because we need to be able to center our squares on that middle. So if you know the width and height of an image, then you can calculate the middle point, the middle index, the middle x value, and the middle y value just by taking half of the original. We need to do something 3 times, so I chose to actually do this with a loop. So I say repeat for size equals 50, 100, 150. Now notice this is getting a little bit like programming language notation. I could have written this more in an English-like form, but sometimes the programming notation is just more compact, and so if I don't think it's going to be too confusing, I'll do it this way. But this might be a little confusing, so maybe I could have phrased this a little more abstractly. And then we have our steps here that are doing the calculations for the upper left and lower right corners of the square, and then I just have a description of what should be drawn. Draw the square on the image using OpenCV with tuples, blah, 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 color and thickness, and so forth. This is also pretty close to code. I probably could have described this a little more abstractly as well. But there's a nice level of detail here, and I think that it's fairly easy to read. That's the goal. All right, what are some other examples we've seen? So here from our in-class activity number 4, this was not labeled as pseudocode, but it is. This first part, it kind of shades into the pseudocode. So it says, replace the to-do comment with a for loop that repeats 6 times with I as its loop variable. So that first part, for loop, repeats 6 times with I as its loop variable, that's kind of the first step of our pseudocode. And then these are the steps that we want to do inside that loop. Define a variable to hold the ith color in the colors list, calculate the center value, draw a filled in circle. Look at this and compare it to the pseudocode I did up above, and you'll see that they're similar in their level of detail, and they're also written in English with a little bit of math notation. Also from in-class activity 4, there was another example. This is actually morally even like pseudocode. One of the things that I hadn't mentioned was that we usually use indentation in pseudocode to indicate what things are part of a loop or a conditional or things like that. So this is supposed to be drawing an ellipse that moves down across an image in a diagonal fashion. And this is really just pseudocode. It's step-by-step instructions for what we need to do. Your job in the activity, if you got to this part, was to translate that into Python. And the last example, this is from in-class activity 5. So we were looking at, oh heavens, what were we doing in this activity? Oh, we were trying to read in all of the images, all of the image files in a folder and display them one after the other. But again, while this has got a few places where it's addressing you as the programmer, for the most part, this is a pretty good statement of pseudocode. So we've been using that all along as a way to describe what we want you to do on a particular assignment. And again, the purpose there was twofold. Number one, we wanted to communicate with you. And number two, we're taking the design task on ourselves and leaving you with the task of turning it into Python, which just makes life easier for you. But in the long run, you want to be able to create algorithms in pseudocode for yourself so that you can create programs of your own imagination and be really creative with them. All right. I'm kind of interrupting myself here because I realized after the fact just how long this total recording was. So I'm breaking the recording here, and we're going to stop and put the rest in another video. So what we've looked at so far is what an algorithm is, what pseudocode is, and why we want to do it. And we've looked at some examples of pseudocode that you have already seen in materials so far. What I'm going to do is stop here, and in the next video, separately, we'll go over some examples of writing an algorithm in pseudocode from scratch. I will see you very soon.